right? Let's say that the mean value is about 10 degrees, right? Let's say it's not. It's minus 15 or something like that. Anyway, so this is the temperature in Moscow. Let me call this M. Okay, so we have this random variable M, which is the temperature in Moscow in 5 years somehow. It looks like that. The mean value is about 10. But now if you measure the temperature in Damascus, right, maybe the average value is going to be 10, but it's going to be something like this, right? I believe so. I don't know. So the point is that the mean value of the temperature in Moscow and in Damascus might be the same. But of course, we are talking about completely different things. Because in Moscow, we go way, way higher and way below, right, zero. And in Damascus, we are about 10 degrees. Well, that's what I believe, right? So the mean value is not enough. The expected value is not enough. We also have to understand how far we are from the expected value, right? So for every moment of time t, so this is time here, for every moment of time, we have to understand how far we are from the expected value. So this distance from here, these distances. We have to understand how far we are from here, and we have to find the mean value of these distances. So look, we have the distance is psi minus the expected value of psi. Yes, psi minus the expected value of psi is this distance right here, and we need to find the expected value of this distance. So the expected value of this. But we have a problem. What is the problem? That what is this equal to? Huh? This. Okay, and what is E of psi? Yeah, that's a good question. What is E of psi? This is E of psi, just right? Because E of psi is a number. E of psi is a constant, right? So again, psi, the random variable psi is a function, and the expected value is a number. This is already a number, so the expected value is always a number. Okay, that's why the expected value of a constant we already proved somehow that is equal to the constant itself. So the E of psi is just E of psi, right? So we have that this is equal to 0. So that's not good. This doesn't give us any information, right? So we have two options. The first option is to take the absolute value of this difference, right? But it's not very nice to work with the absolute values. So let's just take the square. So let's take expected value of psi minus expected value of psi square. So we are taking the mean value of how far we are from the expected value, and then we put this square. And we will call this number the variance of psi. Variance of psi. So we denote it like this, bar of psi. Okay? So the variance of psi give us the following information: how far we are from the expected value. Okay, how far we are from the expected value. So that will define. So that if we find now, so this was M, this was D, Damascus, right? Then maybe the expected value of M equals the expected value of D, but clearly the variance of M will be way higher than the variance of D. Right? And now we have some information, and most of the times this is enough. Expected value and the variance will be enough to completely understand the whole random variable. Okay, most of the times this is enough. So that's what we call the variance, right? Variance. So this is the definition of variance. Now, so one example. Okay, but before that we need to compute. We need to understand how to compute it. So, properties of the variance. So property number one is how do we compute it? And we are going to compute the variance like this. So variance of psi will be equal to the expected value of psi squared minus the expected value of psi and the whole thing squared. Okay, so this is the formula that we actually are going to use to compute the expected value. Not this one. This one is not very nice to work with, but this is way better to work with. Okay, so this is the first one. Second property is that the variance of psi is always greater or equal than 0. Okay, the variance of psi is always greater or equal than 0, and moreover, the variance of psi is equal to 0 only if psi is a constant. Almost surely. Let me just write psi as a constant. So if we have a constant, so the temperature is exactly the same always. So the variance is 0, so we have a constant, okay? So the only case when we have that the variance is equal to 0 is when we are talking about a constant. Because as we already discussed, a number, so for example, 5, the number 5 is also a random variable. Because this is a function, the function is constant, but it still is a function, and it still is a random variable. So in that case, we have that the variance is equal to 0. Otherwise, the variance is always positive. So if the variance in the test gives you -1, something is wrong. The same way that the variance, that the probability is not negative or greater than 1. Okay. It already happened. Someone obtained in some probability 4. Well, you didn't compute till the end. That's why you didn't notice. But yeah. So anyway, we have this and property number 3. Which one do I have here? Yeah, the property, the variance. So if A is a real number, then we have that the variance of xi plus b, so A and B are real numbers. The variance of xi plus b is equal to the variance of, so a squared times the variance of psi. So these are the 3 properties that we need by now. Okay, so let's prove them.